Morning to all. Today I am going to discuss about next part of important chapters in second intermediate. That is the one is atoms and nucleus. Both combined together, you may have two problems from second intermediate. See, in this session, what are the things we are going to discuss here is about Thomson Rutherford Bohr experiment and spectral lines, hydrogen spectral lines. Okay, now this one weightage of NEET and EAMCET here is atom and nuclei, and even both are having a same two questions will be asked, one from the atom, another one is from the nuclei. So two questions you may have this one. This is a short chapters, both atoms and nuclei, and direct questions will be there. 5% of weightage will be there from this chapter. Okay, now next one. Okay, now the next question here is the Geiger-Marsden experiment, scattering experiment. Find the distance of closest approach to the nucleus of a 7.7 mega electron volt alpha particle before it comes into rest. This one, let me tell you what you mean that Geiger-Marsden experiment. See, in this radioisotopes, it will emit radio active particles that will emit a radio particles here is alpha particles. Once it interact over here, it will get scattered in all the directions. With the fluorescent screen, we can observe over here. See what they are asking in this case. This alpha particle interact with the gold foil here. They have given the nucleus of the gold atoms. How closest approach, that's what they are asking here. The closest approach of the alpha particles towards the nucleus, that is about the distance they are asking over here. That one we are going to find out here. Now in this case, let me tell you the first one here is we are going to find out the kinetic energy. In this case, the kinetic energy formula already you know this one. In this case, with the help of even this is similar to the Coulomb's law also, we can find out here. See, from this one I just mentioned here, K is equal to that one here is 1 divided by 4 pi epsilon naught, uh, and this one there are two charges q1 q2 divided by 4 pi epsilon naught will be there, but there r that is r square will be there, but here is two charges. This is alpha particle which is having a 2 electron here, and even a gold atom which is having a atomic number is that number of electrons. That one, see, atomic number and number of electrons, the gold foil, that's one they have mentioned here. This is about the alpha particle, this one is about alpha particle, and this is gold foil, and d is about the distance between them. This one only we are going to find out here. See, from this one, d is equal to 1 divided by 4 pi epsilon naught I just mentioned here into 2 ze square and divided by k here. Now this one already they have given the value, that is a 7.7 mega electron volt. Now you just substitute all the values here. See, from this one I just mentioned here 2 into this one here is atomic number here is 79, and this one into E here is a 1.6 into, that is about the charge of the electron, 1.6 into 10 power 19 the whole square, and divided by 4 pi epsilon naught. This one 4 pi epsilon naught, this one I just mentioned here, 1 by 4 pi epsilon naught will be equal to 9 into 10 power 9 Newton per meter square, Newton meter square per coulomb square. This one Newton meter square per coulomb square. This one here. So in that, instead of that one I just mentioned here 1 by 4 pi, instead of that one I just mentioned as 9 into 10 power 9, and whole divided by what you are having here is k value. K value here is that one I just mentioned here 7.7 mega electron volt. Mega means 10 power 6 electron volt. But while substituting this one, you are going to mention this one in joule, so that see here 1 electron volt equal to 1.6 into 10 power minus 19 joule. So this one mega electron volt 6 already we have mentioned here, and the electron volt here is 1 joule equal to 1.6 into 10 power minus 19. You need to mention over here. Now this one you just substitute here. From this one you can cancel. See, 1 will be cancelled over here in this, and only 1.6 into 1 is there, 1.6 into 10 power minus 19 will be there, and you just cancel this one. See, from here this is 10 power 6 is there, and this one 10 power 9, so remaining here is 10 power 3 is there. So from this 10 power 3 you just cancel this one. This is a 10 power minus 16 will be there. You just cancel this one, 10 power 3. So what are the things is there, I just write on here. 2 into 79, I just round up into 80, and 1.6 into 10 power minus 13, and into this one here is 9 is there, and whole divided by 7.7, I just mentioned as 8 for short. See, always try to, you are going to do in manual method, so you just put in round off method, so that approximate answers you can get here. See, 9 into 2, this one is 18. 18 here, 1 you can cancel over here, that is minus 12 will be there. Now you just cancel it. This is 18 into 1.6 into 10 power minus 12. So this one, if you cancel over here, approximately what you are going to have here is this one, approximately you may have um, around this one will be there. Approximate, if you mention this one, 30 into, I just mentioned here, 30 into 10 power minus 15 meter should come here. So that is 30 Fermi meter. So answer in this case here is this one. Problem here is when the electron in hydrogen atom jumps from the second orbit to the first orbit. Now it is moving from, there are a number of orbit here, from the second orbit to the first orbit. Whenever the electron is moving from the higher orbit to the lower orbit, what happens? It emits some radiations. So the wavelength of radiation here is they have given as lambda. When the electron is jumped from the third to the first orbit, now second to the first, they have given the wavelength here is lambda. If it is moving from the third to the first orbit, what is the wavelength of this radiation? For this one, hope you know about this one. In this case, I just mentioned here. See, this one, if the wavelength of emitted radiation what they have given here is 1 by lambda is equal to z square r into 1 by n1 square minus n2 square here. Now, in this case, lambda is about the wavelength, that one only we are going to find out. But already they have given from second orbit to the first orbit, they have given as lambda. From third orbit to the first orbit, that one we are going to find out here. For this one, see, in this case, it just utilize the same. See, I just mentioned here. So, 1 by lambda will be equal to r z square. That one will be equal to 1 by n1 square minus 1 by n2 square. So only thing, the variation in this here is lambda is going to vary, and this one already they have given, this is hydrogen atom. So z and this one r is not going to change, only changes over on the number. So 1 by lambda, which is proportional to, I just mentioned here, 1 by n1 square minus 1 by n2 square. See, in this case, lambda 1, I just mentioned in the first case, I just mentioned as lambda 1. Lambda 1 value they have given, that is lambda. And lambda 2, I just mentioned here, that one only we are going to find out in this case. 1 by, first one is 1 square, at this one. And here is a minus of 1 by, I just mentioned here, the second one here is, see, this one. So this is already 1 by lambda. So that lambda in this case I just mentioned here, lambda is proportional to. So what you are going to have here is 1 divided by 1 by n1 square minus 1 by n2 square. So that I just mentioned here, in this case 1 by 1 square minus 1 by this one here is 2 square. And for this one you can mention here 1 by 1 square minus 1 by 3 square here. Now you just simplify this one. Lambda 1 here is lambda, and lambda 2 only we are going to find out in this one. See, this one here is 1 by 1 minus 1 by 9 here. So what you are having here is 1 minus 1 by 9, and this one here is 1 minus 1 by 4. Now from this one, 8 divided by 9, 8 divided by 9, whole divided by 4 minus 1 here is 3 divided by 4. See, from this one, 8 by 9 into, if you are taking here is 4 by 3. So from this one, what you are going to have here is 32 divided by 27. So that is lambda. So from here, lambda 2 is equal to 27 divided by 32 lambda. So answer in this case here is this one. Okay, now the next question here is the ground state energy of hydrogen atom. See, the electron of an hydrogen atom in the ground state, that is a minus 13.6 electron volt. In that case, the kinetic energy of electron in that state is what? So all the answers has been given in joules. So you have to convert this one electron volt into joules. See, for this case, let me tell you here. For this one, first one here, a ground state energy already they have given. Ground state energy here is, I just mentioned here, ground state energy of hydrogen atom. So that one I just mentioned here, minus 13.6 electron volt. Now at this state, kinetic energy of the electron. See, kinetic energy of the electron I just mentioned here. Electron here is, see, I just mentioned this one. This is minus E. So this one will come over here. So that is about minus 13.6 electron volt. Now, see, in this case, kinetic energy, I just mentioned here, kinetic energy is equal to what you are going to have here is kinetic energy, that is minus E, that is in ground state. Once you are moving to the ground state to the higher energy state, it should have some energy, so that the electron, whenever it will be excited, means whenever it gets an energy, that energy should be greater than the 13.6, so that it will be moving to the higher energy state. But at the same time, it would not be the stable at that state. Again, it will come back to the lower energy state with release of some energy. See here, in this case, in this case, I just mentioned here, electron volt here is 1.6. See, electron, in this case, the charge of the electron you just mentioned here, 1.6 into 10 power minus 19. You just multiply this one. What you are going to have here is 21.76 into 10 power minus 19 joules. See, in all the cases, what they have given here is, in all the cases, that is in 18, 16, 14 joules here. Now I just round up this value. So what you're going to have here is 2.176 into 10 power minus 18 joules. So in this case, answer here is this one. Now, some case in some other time they are going to ask about the potential energy also. So this is about the kinetic energy, and potential energy here is 2 times of E here. That is 2 into, you just multiply this one twice of this value, or even 2 into 13.6 electron volt, or even you can mention here that is 27.2, see, 27.2 electron volt. That one here is a minus, because that is in the ground state only, so that you have to mention this one in minus only. So sometimes they may ask you this one also. Question here is hydrogen atom emits blue light. So this is comes under visible range. So that means Balmer series. This is quite interesting. You just concentrate here. See, blue light all are visible range. So it is moving from 4 to 2. You are having blue light. If it is moving from fifth level to the second level, what light will come? See, for this one, let me tell you here. See, suppose blue light wavelength here is this one. If the wavelength is decreases, you are going to violet. If the wavelength is keep on increases, you are going to have a red region. So you are, with the help of this one, you are going to find out. See here, in case of Lyman series, it will be moving from 2 to 1, 3 to 1 in all the cases. See here, N1 here is 1 and N2 here is 2. See, like this, they have mentioned over here. That is Lyman series. This is ultraviolet region. But Palmer series, this is visible region. And Paschen series, bracket series, and P-Fun series, all this comes under infrared region. See this one, I just mentioned here, this will comes under UV region. So I just mentioned here, this is UV region, this is visible region, and these three are infrared region. See, in this case, I just mentioned this one. See, with the help of wavelength, see here, the transition is moving from 4 to 2. What you are going to have the wavelength, and the same one 5 to 2, what wavelength will be there? If the wavelength, when compared to this one, if wavelength is decreases, what you are going to have here is violet in color. If wavelength is increases, that what you are going to have here is red in color. See, for this one, lambda is equal to, this is the concept here. See, I just mentioned in this case. See, with the help of wavelength we can mention, or even with the help of energy we can mention here. In this case, E equal to h nu. From this one, nu here is c by lambda, hc divided by lambda. HC are constant. So in this case, this is directly proportional to lambda. See, for this one, what I'm going to mention here is E, which is proportional to 1 by lambda. That one will be proportional to, you just forget about this one. So ZR values and all. So only thing here is, what you're going to have here is 1 by N1 square minus 1 by N2 square. See, from this one, for the first blue region, already they have mentioned here, blue region in this case I just mentioned this one, that is 1 by 2 square minus 1 by 4 square. That one I just mentioned here. The same one here is this one 1 by 4 minus 1 by 16 here. This one 1 by 16. You just take an LCM, common one here is 16 here. So what you are going to have here is this one here is um, mm, 16 means uh, okay, 4 and this one common I just take here 2 square, and you just multiply just like that. See what you're going to have here is 16 minus 4. What you're going to have here is this is 12 divided by 64. So in third table you just cancel this one, this is 4 time, and this one here is sorry, fourth table if you cancel this one, this is 3, and this one here is mm, okay, even 4 3s are 12, and this one here is uh, okay, 18 here. So that one what you are going to have here is 1 by 6. Now next one, similar in case of next one, what color you are going to have here is 1 by 2 square minus 1 by 25. That is 5 square here. See from this one I just mentioned here 100 is equal to 25 minus 4. What you are going to have here is 21 divided by 100. See in this case, this one I just mentioned as E1, and this one I just mentioned as E2 here. See in this one, 1 by 6 here is 0.33 will be there, and this one here is 0.4, right, is around 4 will be there. This value here is around 4. So in this case energy is maximum. See here, energy is maximum for this one. See here, the transitions are moving from energy and wavelength. See, energy is maximum when the wavelength is decreases over here. See for this one, see when the wavelength is decreases, energy is maximum. See, you can understand over here. For this one, here energy is less, here is energy is maximum. See, energy will be maximum only when wavelength is decreases. See from this one, here wavelength is decreases E2, here wavelength is increases. So wavelength is decreases, in this case it will be moving towards violet in size. See here, you can understand over here, I just mentioned this one. In this case wavelength is decreases, so it will be moving towards violet. So answer in this case here is violet. Okay, next important problem here is, you just go through on this one, the ratio of largest to shortest wavelength in the Balmer series. See, this is the direct answer. You always remember this one. In Balmer series, that is about the wavelength of hydrogen spectra. Balmer series means visible range. For this one, what is the ratio of largest to shortest one? See, in this case, I just mentioned here. For in case of a Balmer series, this one I just mentioned here. For in case of a Balmer series, see, Balmer series, for first N1 here is 2, and N2 here is, I just mentioned here, 3 comma 4, and so on up to infinity. Now for this one, here already we have seen the previous one, 1 by lambda, which is proportional to 1 by N1 square minus 1 by N2 square. See from this one, you just mention here, from this one what you are going to have here is lambda largest divided by lambda smallest to 1. So lambda largest here is 1 by 2 square minus 1 by infinity square, and smallest one here is 1 by 2 square, that the immediate one, that is 1 by 3 square here. So what you are going to have here is, this one will become, see, smallest one or shortest one. See here, this is 1 by lambda, so that you can mention over here lambda only you are going to mention, so that you are going to have from this one, this value here is 1 by 4, and this one value here is 5 divided by 36. So what you are going to have here is 9 divided by 5. So answer in this case here is 9 by 5. This is a little interesting subject, little interesting topic. You just concentrate here, but here is two options are correct. You just go through on this one. Say electron in the hydrogen atom makes a transition from N1 to N2. So 1 to 2, where N1 and N2 are principal quantum number of the two states. See, assume the Bohr atom model to be valid. So what do you mean by Bohr atom model? Already you know this one. That is electrons, the number of, see in this case the electrons which are revolving around the nucleus, and inside the nucleus in an atom. If you consider about the atom I just mentioned here, if you consider about the atoms, all number of protons and neutrons are present inside the nucleus, and the electron which are revolving around the nucleus, and the number of electrons are occupied in the first second orbit based on 2n square formula here. So like this, these are all the basic things. If it is accepted, that one we call it as a Bohr atom model. that is about the postulates of Bohr atom model. See, the time period of a electron in the initial state is, see, initial state I just mentioned here, that is a T1 time period in this case. See, time period in the initial state, this one you can mention here, that the first orbit, this one initial state, that will be 8 times of this one, 8 times that is in the final state. For example, this one N1 to N2, what they have given here is T2. See here, in this case, the possible values of N1 and N2 they are asking in this one. See, for this one, before going to that, you have to know this one time period of electron in the nth orbit here is T of N. This is the formula. From this one you just forget about these values, only we are going to concentrate about the principal quantum number and even atomic number. This is about hydrogen atom, so atomic number here is 1, so Tn is proportional to n cube. See, from this one I just mentioned here, Tn is proportional to n cube, or even T is proportional to n cube here. See, in this case, first one you just mentioned here, see here, T1 which is proportional to n1 cube, and similarly this one I just mentioned here, T2 is proportional to N2 cube. See, from this one I just mentioned here, this is N2 cube, right? And this one T1 by T2 I just mentioned here, T1 divided by T2 will be equal to N1 cube divided by N2 cube. See, I just mentioned here, N1 cube divided by N2 cube. See, from this one already they have mentioned here. See, from this topic we just mentioned here, T1 divided by T2 here is 8. See, from this one here, what I'm going to mention here is 8 is equal to N1 cube divided by N2 cube. See, from this one again I just mentioned here, see, this one we can consider a little later. See, this one from here, N2 cube, this is cube here, and 8n2 cube will be equal to 8n2 cube will be equal to n1 cube here. Take a cube root, that is 2 cube, and n2 cube will be equal to n1 cube. See, from this one n1 will be equal to 2n2. So this one is the concept you just understand here. Next one, in this case, see, from this one what they have given here is n1 equal to 2n2. So what are the possibilities are there? For example, if you put n2 is equal to, I just mentioned here, if you put n2 is equal to 1, so n1 here is what you are going to have here is n1 is equal to 2 here. So possibilities here is 2 comma 1 transitions are possible. Next one I just mentioned here, if n2 is equal to 2, so here is if you mention 2, so n1 here is 4. So what are the possibilities are there? 4 comma 2. Is there any 4 comma 2 values are there? Yeah, you can see this one. 4 comma 2 is there. N1 is 4 and N2. See, again you can mention here, if N2 is equal to 3 here. Now N1 here is what you are going to have here is 6. So what you are going to have 6 comma 3. Do you have any 6 comma 3 is there? So for this one, yeah. Third, this one also is there. Next one I just mentioned here, if N2 is equal to 4 and N1 here is 8. If it is 8 comma 4, if it is there that value, so you can confirm here. So in this case answer here is this two. Okay, now the next problem here is any radiation in the ultraviolet region. See here, UV region, this one ultraviolet region of a hydrogen spectrum is able to eject a photoelectron from a metal. See, from the metals you are going to have a photoelectron. So that is a photoelectric effect. Then the maximum value of threshold wavelength what they have given here is lambda equal to 911 angstrom. Then the frequency of the metal is nearly. So frequency value they are asking in this case. See, this is about a photoelectric effect, and the photoelectron have an energy I can mention here. This one E is equal to H nu, where nu is about the frequency here. See, in this case they are concentrating about the frequency. Nu is equal to C divided by lambda. Now C value here is velocity of light. That one I just mentioned here, 3 into 10 to the power 8 meter per second, and whole divided by lambda value they have given, that is 911 into 10 to the power angstrom, means 10 to the power minus 10. So this is angstrom. So from this one you just cancel it here. See, I just mentioned in this one, in this case 10 to the power 8. See this one 3 divided by, I just to round off that value I just mentioned this one here is 1000. For example, to better understand here, this is 10 to the power 8, and here 10 power minus 10, if it is comes over here, that is 10 to the power plus 10. So 3 into 10 to the power of, what you are having here is 10 to the power 18 divided by 1000 here. So if you cancel this one, what you are going to have here is 3 into 10 to the power 15 hertz. See, approximately that is 3. If you put a 3 divided by 1000, what values will be that? That will be around 3. So answer in this case here is 3. An hydrogen atom emits a photon. See here, hydrogen atom that emits a photon corresponds to an electron transition from pi to 1. See here, you just consider about an hydrogen atom. See here, hydrogen atom, that is about the nucleus over here, and around the nucleus you are having a first orbit. This hydrogen atom emits a photon. See, from this one it emits a photon. That one will be equal to the transition of an electron from, similar like some other atom, that transition from, see here, this is n is equal to 5 and 4 3 2. So like this will be there from here to 1, transition from electron from 4 to 1, it emits some radiations. So this radiation and this radiations both are similar. So the recoiling speed of an hydrogen atom is nearly equal to, what they are asking here is the velocity. Recoiling speed is about velocity of an hydrogen atom will be equal to what? See, for this one, in this case, see, both are equal in this case. At what case both are equal? Because of the recoiling property also they have mentioned here. Based on this one, here is the momentum I just mentioned here. The momentum of an hydrogen atom will be equal to the photon transition, which is moving from the fifth uh, n equal to 5, fifth to your this one n is equal to 4. So this one will be equal to the photon of an hydrogen atom I just mentioned here, that is mv. So that one will be equal to, what I'm going to mention here is the photon value will be equal to, I just mentioned as the radiated electron, that is e radiation divided by c. See this one, according to the energy you can mention here, this is constant of mv square, and divided by c, this is also velocity. You just cancel this one, velocity and velocity will be cancelled here. So only thing what you are going to have here is, this is about the momentum. See, this one will be equal to momentum here. See, you just consider about the unit. See, according to this one, e value here is, I just mentioned here, e radiation will be equal to, so energy is equal to e here is, even you can mention this one h nu. Nu is about the frequency, already you know this one. H nu here is a frequency. Frequency formula we have seen the previous one, that is r z square into 1 by n1 square minus 1 divided by n2 square. So this is about the formula here. See, from this one, from this one, see, this is m into v. This v value only we are going to find. From here v is equal to, so h here is about a photon number. So photon number here is, you can mention this one, 6.624 into 10 power minus 34, and minus into r value here is this one, r value 1.097 into 10 to the power 7, and z square, this is about hydrogen atom, so that I just mentioned here 1 square over here, and divided by what you are going to have here is mass of the photon here is 1.6 into 10 to the power minus 27. See this one, this is 27 into kilogram. And see here, and what you are going to have here is, additionally you are going to have this is one hydrogen atom, additionally that n square 1 by 1 square minus 1 by 5 square here. Now you just substitute it, what you are going to have here is 6.624 into 10 power minus 34 here. See this one, 34, I just mentioned here, this is 34 into 1.097 into 10 to the power 7 into 1 here. So this one here is 1 minus 1 by 25, that is 24 divided by, I just mentioned here, this is 24 divided by 25 here. So this one I just mentioned in this case, that is 24 divided by 25. Already you are having, this is 1.6 into 10 power minus 27 here. So once you are going to simplify this one, what you are going to have here is, I just mentioned here, I just cancel this one. See, this is 1.6, right? 1.6, and if you mention this one, if you are going to cancel, this is 27 and 34, you can cancel here. So, and even a plus 27 also you can cancel over here. See, this is 27, if you are going to have, this 2 will be cancelled to this one, 34 will be there, and 24 divided by 25 and 1.6, you can mention this one as see here 6.6 here is, I round of value I just mentioned as 6.6 only 6 I just mentioned here for round of value. This one, this is 1, and this is 24 here, and this is 1.6, that is I just mentioned as 16 into 25. This is 16 divided by 10, I just mentioned this one. So now you just cancel in all the case. So this will be approximately will be equal to 4 meter per second answer. Okay, now next some of the important problems on atoms will be discussed in the part 2. I just give the link on this one. You just subscribe the channels and give your comments in the comment section. And if you are having any doubt, you just share in the comment section. First, you just subscribe it and you just support to this channel, so that what are the things I am going to update in the channel, uh, it will be reached to you. You people please subscribe first.